Hello and welcome. In this video, I am going to show you how to create probabilistic maps of a few subcortical and brainstem regions in baby brains. So this idea was given to me by Siham, who visited a few weeks ago Maastricht, and she wanted to learn a type of analysis that I worked on in the past. Siham is a PhD student in the Brain Lab, which is a cognitive neuroscience research group at University of Barcelona. And she is, in the context of her PhD thesis, was particularly interested in the auditory system of infant brains. So in 2019, we have published a paper together with my colleague Kevin Sitek called Mapping the Human Subcortical Auditory System Using Histology, Postmortem, and In Vivo MRI. This is a shared first authorship paper. And Siham reached to me saying that she has read this paper and she wants to redo a part of the analysis that we have performed in this paper, not in an adult human brain, but using baby brains or like newborn brains, actually, small infants. And specifically, just to give you a bit of the context, what she wanted to do was to create, let's say, a 3D model or a template of some of the areas that she was interested in. For instance, she's interested in inferior colliculus and medial geniculate nucleus, as far as I learned from her during our discussion. And she wanted to more specifically do something similar to our figure 5 in this paper. And that is basically when you focus on the left column, you can see that, for instance, in the middle row, for inferior colliculus region, we create a probabilistic map from 10 adult brains. And this map basically shows us the hotspot of where the inferior colliculus is. Also, we did it for medial geniculate nucleus and some other areas as well, but Siham is only interested in these two areas. Okay, so basically the goal today is to create something like this figure or the inputs that went into this figure, not by using the adult brains, but using infant brains. Okay, so a few things to prepare for this analysis. Siham nicely sent me 10 sample images from the Developing Human Connectome project, DHCP. And now let's have a look at the data. This is the data set that Siham sent me. You can see that there are 10 different infant brains, and these are T1 weighted images. Some of you might notice that T1 weighted contrast is a bit different because these are newborn babies, as far as I understand. And even the T1 weighted contrast, also T2 weighted contrast, is different compared to adult brains. Okay, so these are 10 different brains. And what Siham sent me was also the segmentation that she performed to get the inferior colliculus on each of these 10 brains. So you can see that, for instance, here she nicely labeled the inferior colliculi in this brain together with the medial geniculate nucleus. And also, I think after our discussion, she added the lateral geniculate nucleus here as well. Of course, compared to segmenting these regions based on histology images, using MRI images is a bit harder. You don't have such a high resolution to see these areas very easily. But luckily, these areas, namely LGN, MGN, and inferior colliculus, can be located nicely based on the gross anatomy. They are always at the same type of shape and in a similar location. Unlike, let's say, cortical areas that are much more complicated to work with because there is the high amount of convolution and variation across human brains. So, okay, our task is to do a probabilistic map only in the midbrain and the brainstem around our regions of interest. So you can see their relationships in 3D, for instance, here. Just to give you a few more details about these images, these are infant brain images that are newborn, and the image resolution is 0.5 millimeter isotropic resolution. You can see that the position of these images are somewhat different in each subject. So our task is to register them as good as possible and then use that registration to create a probabilistic map based on Siham's segmentations of all of these 10 infant brains. Okay, so to start analyzing this data set, I needed a reference space that I should, with some confidence, use. And I start searching for it, and I have encountered the infant atlas. I think this is basically like MNI baby brain templates. And in this website, you can see MNI McGill infant atlases 0 for 5 years or 4.5 years, I think. They provide a set of images already in registered and Nifty format that is between different age ranges. And these age of the infant brains are in weeks. I think the most similar to Siham's data is the 0 to 2 weeks of imaging, so the very first one. So we are going to get the T1 and T2 weighted images from here, although I just ended up using T1 at the end. Okay, so just to give you a bit of more structure, I have put developing human connectome project baby brains, infant brains here in a folder called 01 anatomicals. So these are all the infant brain anatomical images that we see here. And on top, we have the ROIs that are manually segmented that we are going to use to create our probabilistic map. And as the third one, just to show you, we have the infant brain templates. I call it like baby MNI. I'm not sure if I name it correctly, but for further information, please read this resource. Okay, so let's have a look at the relevant image from here first. We are going to use the T1 weighted images for the sake of this video. Okay, so this is the T1 weighted infant brain that is already averaged across 108 children, which is, I think, is a good like a reference space to begin with, to align things to when you are creating these probabilistic maps. Okay, exploring this image a little bit, we can see that actually there's a nice contrast to see LGN and MGN in these images. For instance, if I optimize the contrast a little bit, let's say like so. As I work with these areas in the past in adult brains, and since infant brains are not so different at least in the midbrain, I can tell you with confidence that this is, for instance, this little bright blob is MGN, and the right next to it is LGN. And these images are 0.5 millimeter isotopic resolution. Okay, the other area that Siham is interested in is the inferior colliculus, which is basically here. That is that like inferior bump that you see on the back of the brainstem. But anyway, like some details are not so important right now, but we want to basically take this template image and align each of our 10 baby brains to here. However, there's a complication at the beginning because the baby brains that we have are 0.5 millimeter isotropic resolution, whereas this data set, the template, is at 1 millimeter isotropic resolution. So first step that I would like to do is to upsample or resample this template from 1 millimeter to 0.5 millimeter isotropic resolution. Just to cut this part short a bit, I'm going to show you that I have already written a script to perform it, and I'm going to share these scripts below in the video description, so you can see exactly how I am upsampling the template image from 1 millimeter to 0.5 millimeter by looking at the video description. I'm going to go a bit fast over these scripts, so don't worry about it. But basically, in this script, we are giving an input that is our 0 to 2 week old infant brain T1 weighted template image, Nifty. We give it an output directory and determine a few things, and it just upsamples for us. Okay, this is a Python script basically. And I assume that you know how to use Python for the sake of this video. So, okay, now let's navigate to our scripts folder, which is here. And you can see that I have some other scripts that will be used in this video tutorial. And let's run the first script, Python upsample MNI template. Okay, now it is running. You can see that it prints the previous and the resampled image sizes, and this should be exactly twice the amount of like voxels in each dimension that we have. Okay, so it gave an output. The output is written inside the upsample folder that I have created inside the templates folder, and it just has the suffix resamp 0.5 millimeter. Now let's load it here. Okay, here is the image. I'm using ITK Snap for this video. And for instance, here at information, we can see that our XYZ spacing is now instead of 1, 0.5 millimeter. So we have successfully upsampled our T1 weighted template image. Okay, now let's start registering the baby brains to this template one by one. To do that, I'm going to my anatomical folder. Okay, I load it as an additional image. You can see that the brain is quite a bit far and a bit smaller. But the registration step should account for this difference. Okay, so now let's navigate to the tools and image registration. And here there will be like two steps that we perform. First thing we need to do is we need to put roughly our infant brain image to the same area as the template image. To do that, basically I can go to the manual registration menu of ITK Snap and click on interactive tool. And here I can bring the brain roughly to the same location. I usually try to target the anterior commissure. Like I click on the anterior commissure, like roughly, and then try to bring the other images anterior commissure to the same area. Let's say like so. I mean, roughly. We don't need to be so precise. Once this rough registration is done, the second step is actually quite important because we don't want to optimize our registration for the whole brain. Our regions of interest are very specific. That's the midbrain, mostly inferior part of it, like medial geniculate nucleus and surrounding area, and inferior colliculus in the brainstem and the surrounding area. So, okay, to optimize the registration only around those regions, there is a very handy tool in ITK Snap that we can use. We can go to the segmentation menu here, select the 3D brush, make the brush size maximum. And first, maybe let's find our, just to show you, the medial geniculate body and lateral geniculate body area that is here, these two blobs. And now I'm going to create a mask around that. So you don't need to be so precise, you just need to get enough contrast there, let's say. Okay, like so. And the second area that I would like to optimize my registration is the inferior colliculus, which is basically included there, but we can extend our mask a little bit more there just to make sure that the registration algorithm considers these regions while minimizing the registration cost metric. Okay. And maybe let's include a bit more of the midbrain as well, because there is good contrast there that can help us, that can help the registration algorithm to find a good fit across brains. And in my personal experience, the easiest way to first proceed with this type of probabilistic map generation is to use affine transformation before you go into nonlinear registration steps that I'm not going to talk about in this video. So I'm going to only use 12 degrees of freedom affine transformation. And I think it is good enough for nicely registering the midbrain and brainstem regions in most of the brains. Okay, once our registration mask is drawn like so, I'm going to save it. Just call it reg mask. Okay, now the second important step is that we enable the use segmentation as mask in our registration menu. And we change our transformation model from rigid to affine. Now let's switch to our infant brain that will be registered to the template. And I tinkered around with parameters a bit. I think what works the best is from 8x to 1x. These are different search levels for the registration. And once this is set, I'm going to click on Run Registration. And let's see what will happen. So you can see that the registration algorithm is now stretching the brain in different directions, matching two images based on mutual information similarity metric. We only within the segmentation that we have performed, only within the red area. Of course, like our task is not to register the cortex, so I am going to just completely ignore the registration in the cortex. Okay, so it is done. Now let's see whether our registration worked well enough. And to judge that correctly, you might want to adjust your contrast a bit between these two images to make them more or less match with the contrast. And okay, let's see. I'm using brackets to quickly switch between first and the second image in ITK Snap. Okay, I think the registration is not too bad. And maybe what we can do to tweak it a bit further is to run it again, but starting from a less coarse level. Let's say 2x to 1x. So this will, in some cases, this can optimize the registration a bit further. Okay, I think this is a bit better. And I'm only judging my registration quality in this red region. I'm not looking at the regions beyond that. That's an important step. Okay, I am happy with this registration for now. So for the sake of this analysis, that will be the, let's say, the initial or simple solution to this probabilistic map generation. Let's say that we are happy with this affine transformation and let's proceed with the other brains. But first we need to save the registration affine transformation matrix. And here you need to make sure that you save it as a convert 3D transform file. And let's call it with the subject's ID. And let's call it to template. So basically here you can see that our first affine registration is done. So now I'm going to stop talking and just record myself going through these 10 infant brains and registering them one by one. It is important to not do this step automatically, in my opinion, because these infant brains are quite at different positions. So you need to initially align them first for a better registration performance. And of course, I will be doing quality control while the registration is running and resulting in a registered image. So I think it's very important in such data sets to really do like a hands-on quality control. That's why I'm not going to just make a script and run it for registration for all the subjects. So and just to make a point that this will not take too much time, I'm going to record myself going through all these 10 brains. Okay, let's continue registering. Okay, I'm going to close first and put the second brain here. Okay, same stuff. First I can adjust contrast a bit to see the brain. Then I go to anterior commissure roughly, and I find the anterior commissure in the second brain and position them on top of each other roughly. Once I'm happy with this initial alignment that I have done manually, I'm going to go with the 8x to 1x and just run registration now. Okay, this is actually pretty good, I think. Okay. Third subject. Okay, third one is done. Let's go to the fourth brain. also done. Let's open the fifth brain. Adjust the contrast. Find anterior commissure. I think this has some vein, a big vessel here. Okay, I think it's good enough. Okay, sixth brain. Just the contrast. Find anterior commissure roughly. Use the interactive tool. Okay, I think this one's pretty good. Yeah, this one's pretty good. Okay. Strongly. Okay, let's continue with the next brain. Just contrast. Interior commissure. Not too good. It's fine. Let's save it. I mean, I'm saying it's fine because for this a simple method of just using affine transformation, I think it's fine. If you want a bit further than this, then we need to look into nonlinear registration methods. But maybe before we go there, we need to first establish a starting point using this simpler method. That's the point of this video. And maybe in the future, if Siham wants more help, I can show the more complicated one. Anyway. Template. Okay. Last three. Let's go. Just contrast. Find anterior commissure. Okay, I think it's pretty good. Let's save it. Okay, next. Not sure if this did a good job. Let's see. A bit more. Okay, this is better. Interior calculus. I think it's good enough. Okay, good. Okay, and the last one. Let's go. Okay. Okay, I think this looks good enough. Okay, let's proceed. Okay, so now we have created 10 registration affine transformation matrices. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, let's put them in a new location. And now let's use them in the next script. So you will find the scripts below in the video description. Okay, so now I went to this second script that is called 02 apply registration.py. And here I am basically putting all my newly created affine transformation matrices. I'm using Sublime text editor for those who are interested in that. Now I will put the input anatomical images. In Mac, the easy way to copy all these paths at once is to use Command Option C when you selected them. If you do so, it will copy the path completely. Then I'm using Control Shift and arrows to basically create multiple cursors and edit multiple lines at the same time. And now I will complete this script, entering my paths to this script so that it runs correctly. Okay, this script basically takes a reference input, and that reference input should be our upsampled baby template. Yes, correct. Then we put our anatomical images that will be registered. And once this step is done, I will explain why we had to do it. And the next part is to use the affine transformation matrices, and the subject IDs should match correctly, otherwise they will apply the wrong registration to the wrong subject. I think they do match looking at them. And we give it an output directory. So this step can be done using many software, but the one I'm using here is called Greedy. And just for reference, you can see Greedy and the details of it here. Just stop the video and have a look at the details. And here I'm basically using its affine registration example wrapped in a Python script so that I apply it, the registrations once I have determined them, easily to the different number of input images that I have. Okay, so now let's apply python 02 apply registration.py, and I'm now calling my Python script. Okay, now let's wait a bit and see the result. Our results should be coming to apply registration folder 05. Yes, there are some residuals that I was tinkering with before shooting this video, so I will just remove them. Okay, finished. So now we have all our anatomical images registered to the template, and we can double check that by loading these images. For instance, see, it's already in the same position for the region of interest that we are interested in. Let's load another one, and maybe another one, and then maybe the last one. Okay, so as you see, the brainstem and midbrain is rather nicely registered. Ignore the cortex. Okay, so once you check all these 10 brain images that they are applied correctly, each registration, we can use the next script that is basically taking all these registered, template registered anatomical images and creating an average image from all of them. I like doing it just to make sure and double check the registration, and also have my own, let's say, template. Okay. That later I'm going to use to overlay my probabilistic map on. So I entered my registered, the template registered T1 weighted images. I give it an output directory and I determine an output name. Simply, I just call it subject average here for the sake of demonstration. And now in the same way, I'm going to execute this Python script called composite. And this will create a new output in the composite. Yes, it's written. And now let's have a look. So you can see that this is now our affine transformation midbrain registered 10 infant brains averaged. And of course, as we mentioned, we should ignore the cortex. Like we didn't optimize our registration for the cortex, right? So there is this muddy visual around the cortex, but we don't care. We are looking at the subcortex. And in the subcortex, I think it did a pretty good job. And in my personal experience, I know that the affine transformation in most cases is good enough for the subcortex registration. Okay, so here we can see the subcortex. I can, from even this distance, recognize the area of the lateral geniculate nucleus here and medial geniculate nucleus there. And I can also detect the inferior collicles, these two bright bulbs here. Okay, just to double check, overlay it with our MNI template. Yes, there's a good overlap. Let's adjust the contrast a bit to make it a bit more visible. Yes. Aside from the cortex, the brainstem and the midbrain is, I think, nicely registered. Or good enough for our purposes, let's say, without claiming too much. Okay, so once we are completely sure that we have the right transformation matrices that are applied to the right anatomical images and they give the right output after doing all this quality control, now we can apply our registration transformation matrices to our segmentation. Okay, so just to show you a couple of them. So these are the segmentation files. So you can see that it is just a image where Siham manually labeled, I believe, 6 different areas: inferior collicles left, right, medial geniculate nucleus left, right, and lateral geniculate nucleus left, right. And you can see that different brain images have these areas at different regions because this before the registration step. So now I'm going to take all these segmentations of our regions of interest, and I'm going to apply my transformation matrices on top of them, or on them. So there is something to consider, an extra consideration if you wish here. I have entered my inputs correctly, and now I'm going to input my affine transformation matrices. I can copy the previous script. Again, like you can find these scripts exactly as I use right now in the video description, linked in the video description. I give it an output, I give it a reference, that's the correct reference. Let's copy from here to make sure. Okay, so now the difference and why I use actually Greedy for doing this is that Greedy has a nice interpolation slash resampling option or mode that is called the label mode. And this is exactly designed for applying registrations on labels or segmentations. As in our case now, we have this manually segmented integer valued image with just 6 different values plus 0. And we want to apply registration on top of it, but there are a few like concerns that we need to make sure. For instance, the end result should only have those 6 labels that we have initially, right? We should not have something between 0 and 1, let's say. If the label is 1 and if it's in the border with the apply to the registration, if we are not careful and if we use like a standard image registration or the image resampling method like linear interpolation or cubic interpolation and so forth, we will generate values that are not our integer valued segmentation file or label file or ROI file. Whereas the nice option of Greedy is that there is this label mode with a parameter that you can put here, and it gives us a nice registration option that is designed for registering labels. And you can learn more about it by going to the Greedy's page, documentation page, and see this link on the left side, applying warps to images and segmentations. Here you can find a bit more information about this label mode that I'm using. But this is a critical step, so pay attention to this one. Okay, once we are ready, now we are going to execute this label apply registration to labels. Okay, I simply called my script that is now running Greedy in the background and applying this label apply registration to each segmentation file. The outputs are coming here. Now let's have a look one by one by loading all of them. Okay, so now we can see that we can zoom in and I can browse through different images to show you that these are all the segmented files. Okay. So maybe there is one detail that I notice right now and Siham should know about it and maybe work on it. And that is, it is actually important to use the same label across different brains. For instance, if you call the left inferior colliculus label 1, you should always call it 1 and not like 1 in one subject and 3 in the other subject. I think she did do it consistently somewhat, but not exactly. So maybe this is something to improve. Yeah, I see that in some images, the labels are slightly different. It's okay though, for creating the probabilistic map, this is not a big issue because of our last step. Now we are coming. Once we have registered the ROI files to our template. Now I'm going to create finally the probabilistic map that is based on affine transformation that is optimized for the midbrain and the brainstem around inferior colliculus and medial geniculate body. Okay, so you can see that the inputs are my registered manually segmented images. I have an output directory and an output name. I simply call it subject average probabilistic map. And the important part of this script that you can, of course, download and look at it in detail, and why we don't care, the ROIs are labeled maybe a bit inconsistently across subjects, is because once we read all these ROIs, we just binarize each image anyway to create a probabilistic map. And hopefully, once we run it, the result will be clear. But that's why we don't care the, at least in this script, ROI is being labeled with different integers across different brains. For doing like other things, they need to be consistent, but not at this step. Okay, so now let's run it. Composite for probabilistic map. And now let's open ITK Snap. And let's first load our template, the MNI template. Oops. Now let's overlay on top our own sample size average, this average of 10 baby brains. Just adjusting the contrast a bit. Okay, and finally, let's put our probabilistic map on top. Okay, so now we are not seeing much, but once we zoom in, you will see that there is this gray cloud. We can click inside them and, for instance, read the value. You can see that there are some boxes, for instance, all the subjects overlap. It is 1. So there are some boxes that's 0.9, which means that 9 brains overlap there with regards to the inferior colliculus segmentation and so forth. So one nice visualization method in ITK Snap is we can show this as an overlay and go to the contrast menu and give it a different color map, let's say hot here. And we can change our minimum to, let's say, 0.1. And once we do that, maybe we can a bit more nicely see our probabilistic map on the template that we have created ourselves, as well as the MNI version of it. Yeah, I'm using W to toggle between transparency of the probabilistic map. I'm using brackets to change between MNI template and our own average template, let's say. Like you can see that they are very similar in the brainstem. And we have our probabilistic map visualized here. And of course, although they are not labeled specifically, I know that more lateral one is the probabilistic location of the lateral geniculate nucleus in these infants, and there's MGN, medial geniculate nucleus, in the more medial part. Going a bit further, I see the inferior colliculus there. Okay, so basically, this is how you reach to figure 5, panel left. So we created basically the same maps. And I think this is a good starting point. I will stop here and send this analysis example video to Siham and see how it goes, whether this is useful to her or not, and maybe in the future continue with ideas that build on this. Thanks for listening and have a good day.